So solid, liquid, gas, melting or freezing line, liquid vapor line, boiling line. Most materials have a positive derivative of the pressure temperature coexistence. Liquid water is special because if you look at the freezing curve or the freezing line or the melting line, it has a negative slope. And so we had a discussion about this, and this took us back to the Gibbs-Duhem equation, which allows us to relate the derivative of the pressure with respect to temperature in terms of change in entropy, change in volume. And this is why when ice melts, it contracts, and why ice floats in water. Okay? Okay, so that was the phase diagram, and then we started a discussion about digging more into the pair correlation function. So the pair correlation function, which many of you computed already in either the Monte Carlo molecular dynamics, is a probability distribution that allows you to see how structured your substance is. It allows you to study how structured your liquid is. It also allows you to see or compare going from a solid phase to a liquid phase to a gas phase. And so this is how the typical pair correlation function looks like for water. Okay, so this tells you that there's a higher probability of finding a hydrogen bond, the nearest neighbor, and then as you get further and further away, the correlations go away until you go to 1, when there are no correlations between the pairs of particles. So, is this property special for liquid water only? Okay, do you see structuring, long-range structuring only in liquid water? So that was the question that we asked yesterday. And so this is a question people who study the theory of liquids have been thinking about for a long time. And one simple way you can answer this is to consider two simple substances. Leonard-Jones liquid, so it just has the I to the 12 and I to the 6, so no electrostatics, and hard spheres. So hard spheres, I remind you, it looks like this. And this point here is sigma. Okay, so I have an infinite potential below some value, and then it's 0. Now you can ask, I have particles interacting through hard spheres. Do they exhibit any short-range structure? Okay, so you could compute a pair correlation function for a Leonard-Jones liquid and also for a hard spheres. And the question is, do you see structuring in a hard spheres and in a Leonard-Jones liquid? Well, of course you know better than anyone that Leonard-Jones liquids, of course, exhibit short-range structuring, but also hard spheres. So this is the pair correlation function between hard spheres. And you see, okay, there's 0 probability of finding the particle below 1 because of this. And then you see some structuring. Same thing with Leonard-Jones. So short-range structuring, at least qualitatively, isn't due to attractive interactions. It's more due to random geometrical packing. Okay? The details of the magnitude of the peak position, how long range they are, of course, that will be affected by things like electrostatics in your system. But qualitatively, you see that both both systems, one with attractive interactions, another without attractive interactions, still has this structure. Yes, that's interesting. Okay, so you can learn a lot from these simple liquids about more complicated liquids. Okay, so that's what we discussed yesterday. And then finally, we more formally introduced what exactly the pair correlation function is. Okay, so in principle, one would like to compute the probability distribution of finding all the n particles at their n positions. This would be a high-dimensional probability distribution. Okay, but this is not very useful. It's very difficult to interpret a very high-dimensional probability distribution. If I have 10 to the power 23 particles, what do you do with that? Right? So you want to reduce the dimensionality of your problem. And the way you do that is by the pair correlation function. So I want to ask, what is the probability of finding one particle at position R1 and another particle at position R2? And that's what goes into the pair correlation function. Just remind you that in the classical framework that we're looking at, the pair correlation only involves the configurational part of the partition function. Okay, so I'll go very quickly through this, but basically, in general, you have an n-body probability density, okay, of capital N particles, and so the probability of finding n particles at their particular R1 to Rn positions is just given by a multidimensional integral where you integrate out all those positions from n plus 1 and higher up. So the pair correlation function, which is R1, R2, is from R3 and above. Okay, that's what, when you calculate or when you compute a pair correlation function, you implicitly are doing this step. Okay, you don't explicitly do it, but it's implicit in the way you do the construction. And so the G of R is constructed by first considering the situation. If I consider two particles go to infinity, or the distance between them goes to infinity, then this n-body density can be written as a product of the individual probabilities. Okay, and the G of R, this is an n-body G of R, is just this joint probability divided by the product, this guy. So you can see clearly here that when all these guys go infinitely away from each other, this becomes this, and so the ratio becomes 1. And that's why the G of R, when it's normalized correctly, will go to 1. Okay? Okay, so that's Gn in general. What we typically do is look at G2. And so this is G2. So the probability of finding a particle in a homogeneous system anywhere in my box is simply the density, so the number of particles divided by the volume. Using the definition that I showed you earlier on, I get this two-body density divided by their individual probabilities, and this is just rho squared. And so G of R is this guy here. Okay? Okay, so, well, why is the G of R such an important quantity? Why have we spent a lot of time trying to study it? And so this is where we stopped yesterday. If you want to study different phases, you have a system that's undergoing some, at different temperatures and different pressures, and you want to study the state of matter that it's in, the G of R is a very easy way to see whether it's in a solid, liquid, or gas phase. Okay? Okay, fine. Okay, so that's where we stopped yesterday, so now we continue from here. So, so for a system made up of one type of particle only, let's say a Leonard-Jones liquid, so the total potential energy of my system is the kinetic energy plus the potential energy. Let's assume that my potential energy is written as a sum of pairwise interactions. Okay, And so the total potential energy goes as this. Okay? So the average potential energy is this times the Boltzmann factor. Okay? And so this simplifies to this. Okay? And now I'm going to do what I did in the 3 slides ago, which is I introduced this integration from the third particle and above, because that's what essentially I'm doing here. Okay, so I can introduce this. And why do I do this? Because this then allows me to write, to introduce the pair correlation function. Because now I can introduce the two-body density. So the two-body density is then written as a G of R. Okay? And so now you see, so okay, there's an n squared v squared here, which comes from the rho of this guy. Because remember, this is this divided by rho squared. But now you see from here that for a system like a Leonard-Jones liquid written, which can be expressed as the sum of pairwise interactions, if I know the G of R, I can compute the potential energy of my system. Okay? So, in general, what you will find is that many thermodynamic quantities can be written as some type of integral, a radial integral or an integral of a radial integral involving the derivative of the potential or the potential itself and the G of R. Okay? So this is an extremely useful quantity. The same goes for pressure. So how many of you in the numerical 1 class, no 2, did you do this exercise of computing the pressure for a pairwise interaction? I gave it in my homework. Maybe, okay, anyway. So it was one of the assignments, which was to compute the pressure for a system of n particles which only has pairwise interactions. Huh? No, analytically. Yeah. So you can go through a very similar exercise starting from the derivative of the partition function of the pressure with respect to partition function, and what you end up finding is that the pressure is a function of an integral that involves the G of R and then the first derivative of the potential, which is the force. Okay, this is the virial. Okay, so another reason why for another thermodynamic quantity the G of R becomes very important. You can also compute entropies from the G of R. And so the excess entropy, which is defined as the entropy relative to an ideal gas, the idea here is that you can take the entropy of an n particle system and do some type of Taylor series expansion in terms of number of particles. So you can compute the 2-body terms, the 3-body terms, 4-body, etc. And so I'm not going to go through the derivation. It's a very similar exercise as what was in the potential energy derivation. But again, you can show that the 2-body entropy is an integral of something that looks like G of R log G of R. So you see that you have something like the entropy in there. Okay? So this is like the translational entropy. So using G of R log G of R gives you information about the translational entropy between the particles. Okay? And then finally, I think you all know this now. The other reason why the G of R is very important and interesting is that it also allows you to infer the average degree of coordination around a particle. So by taking the radial integral, I can tell you on average how many particles are forming neighbors at a particular distance. Okay? Okay, so, so in the area of computer simulation, people invest a lot of time trying to reproduce the pair correlation function. They want to reproduce it and make sure that it compares well with an experiment. And I hope you can see now why. That's, if you can get the G of R correct, you get lots of thermodynamics for free in some sense. Okay? So you really have something that you can trust and that you can use the model then to do other predictive things. Okay. So one thing I haven't mentioned, so these are, G of R's of water. So in water I have 3 G of R's. I have the oxygen-oxygen, oxygen-hydrogen, and hydrogen-hydrogen. There's an assumption I'm making when I construct this G of R. What's missing from this? In light of what I told you about the n-body density and so forth, what information is missing from this? So in a pair correlation, I'm only looking at two-body correlations. I'm missing out higher order correlations. In a dipolar liquid, like water, one important thing that will certainly affect the properties of the liquid is its dipolar correlations. So I have dipoles on the waters, and the dipoles will orient relative to each other. And so this is just an example of a study where what they do is they sit on different water molecules and they measure cosine theta. So cosine theta is the angle between this dipole and this dipole here as a function of distance. So when I'm infinitely far apart, these should be completely decorrelated. And the question is, when I come closer, what is the extent of those correlations? And what's rather peculiar and interesting here is that what you see is, so they do a finite size scaling effect or sensitivity. They start from small boxes and they go all the way to very big boxes. And the f of r is defined by this quantity here, but it's essentially a normalized cosine theta as a function of distance. And what you see is that at short range, as you expect, there are correlations, and then it goes away. So these are orientational correlations. Okay? And when they go to even bigger boxes, there's a very, very weak correlation, even when you're out to 25, 30 angstroms. It's a very weak effect, but it's there. And so all this is saying is that in a liquid like water, defining a dielectric constant, so a continuum mean field type of model, would not really make sense until you got to the length scales of 25 to 30 angstroms. Okay, that's because on those length scales, you still have dipole correlations. And of course, the mean field picture, the continuum dielectric picture, neglects all these types of correlations. And that's fine, as long as you're on some particular length scale.
Excuse me.
Yeah, please.
Dipolar correlation means if there is a certain molecule here with a certain orientation, what is the probability that at R there will be another molecule with same orientation?
Yes. Yes. Okay. So are they aligned? Are the dipoles parallel or anti-parallel?
So shouldn't the correlation go to negative?
No, because when you're infinitely far away, you'll have equal likelihood of being like this and like that.
Okay, that is 0, but
yeah?
Isn't there any distance at which it is like opposite?
Well, that's a good question.
I think there is
there is a small, there's a small effect, and this is, let's see, at 4 angstroms, which is, yeah, so, okay. So in water, because you have, you get loops in a network. And so there are some waters that can orient in the opposite direction. But generally speaking, because of the tetrahedrality of the network, it pushes them all out in the same direction.
So one more thing.
Yeah.
We have, like in this plot, the dipolar correlation has been plotted against R. Mm-hmm. Wouldn't it be more better if we could fix R and plot it along theta? That is at a certain R, maybe at a certain R, because it is a conditional probability.
Yes.
Because it is a probability calculated over the radial function.
Absolutely.
Because if there is no particle, what about like dipolar correlation in the
yes.
first place? So in the first place there has to be a molecule.
Yeah.
So I was thinking maybe we should take a certain peak where there is a high probability that there is a molecule, and then see how it differs with theta.
So, okay, so basically, okay, so let's say this is the GOR.
Okay.
So
You go there.
I go there, and then you're saying, let me measure cosine theta. The distribution.
Let's measure f theta as theta. For example,
so the probability distribution of
the probability distribution of having a certain theta at that R.
Ah, yeah, sure. Isn't that already encoded in this? So this is f of cosine theta as a function of R. It's f of cosine theta as a function of R. So we're going along this, and we are histogramming the distribution of f of cosine theta in this bin. Then I move the bin, I measure it again. I move the bin, I measure it again. Relative to my reference. So I don't see why you think that will give you more information or different. Like, I don't see the difference.
In this case, we have gone to a certain R, and we have calculated what is the probability that the dipolar orientation will be same as the origin.
Yes.
I was thinking, why don't we go to a certain R where there is a, let's say, high probability of having a particle.
Okay.
Some peak.
So here.
Yeah. And then calculate what is the probability that the orientation will be of certain theta. That means we go fix R.
Yes.
And then we see the distribution of
f of cosine theta,
with theta.
What do you mean with theta? I don't understand.
For example, like at a certain R, it may be completely down, or it may be completely up, or it may be at certain orientation.
Yes.
Obviously, like maybe completely down or completely up is a little fixing the origin.
So for example, this guy here at 2.8, there's a high correlation.
Yes.
Okay. Okay. It doesn't tell you
what are the
possibilities of cut. Agreed. This I agree with. Yes. So yes, one could constrain yourself at this point, and then look at the distribution of theta. Yeah. That's a good idea. Yeah. It would tell you more about whether it's parallel, anti-parallel, or isotropic at that point. Yeah, I agree. Okay, questions on this before I transition into something else? Okay, good. So now we're going to go to a bit more of biology. Well, sort of. Okay. So what I've tried to do is to give you some background in at least the way people think about liquids in general, and more basics about water. But now we're going to come back and study some other processes related to water that are relevant to biology. And one of them is osmotic pressure. Okay, so osmotic pressure is something that our ancestors knew a long time ago. And so people used to sit around the fire, and they used to they'd kill animals, and then they'd want to, preserve the meat. And how do you preserve meat? Well, you cure it. You dry it. You put salt in it. And why? Why does, you said smoking too. Okay. Why does drying or salting allow for preservation of food?
It takes water out.
It sucks water out. So you've got bad bacteria. Osmotic pressure will create a chemical potential of the water difference between the salt and the water inside the cells. Water is withdrawn, and the bad cells die. Okay, this is why salt preserves food. Okay, so and drying preserves food in general. Again, because water is needed to sustain the good stuff and the bad stuff. Okay. So that's osmotic pressure. So what is osmotic pressure? More seriously, so I have a solution, a box. Let's imagine that I had a box. I have a semi-permeable membrane. It allows water to go through, but not a bigger species like maybe a protein or a salt. Okay? And let's say on the left side I had some concentration of a protein, a low concentration, on the other side a high concentration. Let's also imagine that I was able to measure the pressure on each side of the reservoir. So I start my system in this condition, and intuition and your own knowledge tells you that over time the water will equilibrate, will move back and forth until the chemical potential of water in the two sides of the reservoir is the same, and you get an equal concentration of albumin or this protein on both sides. What this effectively amounts to, if you were able to measure the pressure on each side, is that there would be a pressure difference. Again, this is osmotic pressure. Okay, osmotic pressure is something that is very important in biology. Okay, because remember, we talked a lot about cells, water, ions, concentrations, membranes, flux of water, flux of proteins. All this requires osmotic pressure to work correctly. Okay, so just some definitions. Oops. So if I have a cell where the concentration of the solute in the cell is equal to that outside, it's called isotonic, which is this guy here. If the concentration of the solute is high outside the cell, it's hypertonic, and it's hypotonic if the concentration is high inside the cell. When you put I think you put a potato the simplest experiment, you put a potato in salty water, and you come back the next morning, and the potato is soft and mushy. And that's because of this. So, if you put cells, red blood cells, in pure water, they'll inflate and burst. If you put cells in concentrated salt solution, they will shrivel and shrink. Okay. So where does this come from? Well, there's this a chemist who came up with this empirical relationship known as the Vant-Hoff formula, which correlates pressure with concentration. Pressure is basically proportional to this concentration. And this is actually quite analogous to the ideal gas equation. Okay, so it's not surprising that there is this sort of relationship between pressure and concentration, because you see pressure is N over V, or is proportional to N over V. Okay, so this is more empirical stuff that one might have seen from chemical thermodynamics. But now let's try and come up with this formula, again by a very simple model, looking at water molecules and solutes on a lattice. If I look at my lattice model, can I infer how the pressure difference would be related to the concentration? Okay, so that's where we want to go.
What is that?
I is some constant that depends on the type of solute that you're dealing with. So it's an empirical, there's some empirical relationship that different solutes will have a different constant of proportionality. Okay, that's not dependent on the concentration. Okay, good. So, what's the system? Just like the real experiment that I showed you, I have two sides. I have left side, right side. Water molecules, small spheres, and these big guys here are proteins or salt. There's a membrane in between, and the membrane has small holes which only allows water molecules to go through, but not the big guys. Okay? So that's the system. And we're going to put this system on a lattice. Okay, so just like in the lattice model that we had for the ligand binding to the protein, now I have water molecules and other solutes on a lattice, and they can occupy different sites on the lattice. Okay? Okay, and what we want to do is, because the osmotic pressure is related to the chemical potential of the water on these two different sides of the semi-permeable membrane. So I need to be able to compute the chemical potential. So that's the system, solute, solvent. And we assume that they occupy sites on the lattice, and we're going to count the number of ways I can arrange solute and water molecules on the different sides of the lattice. Okay, because this is going to help us get at the chemical potential. Okay, so here are the variables. I have NH2O water molecules, and I have NS solutes. I'm going to assume safely that the number of H2O is much bigger than the number of solute molecules. Okay? And this number of water molecules is 10 to the 10, number of solute molecules is 10 to the 6. So this is a very fair assumption. Okay, so the chemical potential of any substance is the molar derivative of the free energy. Okay, so the total free energy with respect to either the solute or the water. I'm going to define the free energy of my system as essentially the excess chemical potential of a water molecule, so of a single water molecule. And so the total free energy associated with all the waters is this guy times the number of waters. I have a solute energy, okay, because from the protein of the salt, each of that contributes E of S. And so they're NS solute molecules, so the total energy is this. And then I have an entropic term. I've made an assumption here. The assumption here is that this works as like an ideal system. There are no interactions between the solute and the water. Okay, but let's see if just using an ideal system, do we understand where the origin of the osmotic pressure comes from? Okay, that's the thinking. Okay, so I need to compute this mixing entropy. Okay, so the minus TS term. So how am I going to do it? I turned the slide too quickly. Shush. Don't say anything. Joe? I want to compute, how do I compute this S mix? So I have a lattice. The lattice can be occupied by waters or solute. I have NS solute guys and H2O water guys. So what is it?
Of the N solute times the N
Times or plus?
so you say you have solutes and
Water. I have solute and water.
okay, so the total number of particles will be 2.
Yeah.
Factorial divided by the separate number of particles.
The product of NS. Okay. Fine. So that's this guy. Okay. Now I can apply Stirling's rule and also use the fact that NH2O is greater than NS. Okay, so I can go through the math and you can please check it for me if I've done it correctly. And I get something like this. Okay, so I've made an approximation here. And the approximation is that NH2O is much bigger than NS, which is a fair assumption to make. Okay, but if I make that assumption, I get that the mixing term looks like this. Okay, so now I can plug this into my total free energy of my system, and I see that it's a function of NH2O and NS. And so I can take derivatives of this with respect to NS and NH2O. Okay, and if I take it with respect to the solute, I get what you've probably all seen before, which is the expression for the chemical potential of a system, which is this E of S term plus the ratio of the concentration with respect to some reference. Okay, so standard molar conditions. Okay, so this is the chemical potential of a solute in the solvent. Okay, fine. Now I can do the same thing. I take the derivative of this with respect to NH2O. So I get this term here, and then there's some terms that come from this part. And you get this guy here. So the chemical potential of the water as a function of temperature and pressure is given by this reference free energy or energy of a single water minus NS over NH2O times kBT. Okay, Now, let me assume for a second that there is a pressure difference between the left side and the right side. So remember, there's a chemical potential for the water to be on, let's go back to this. I'm trying to come up with an expression for the chemical potential of the water on this side versus the water on this side. Okay? The chemical potential of the water has changed because I have solute around in there. It's a concentrated solution. The chemical potential has to change so that the chemical potential on the left side and the right side of the water is the same. What this implies is that there must be a pressure difference. Okay? So, but again, I'm looking at chemical potential of water on the left side versus the right side. So let's assume for a second that I have a pressure difference. So I can say, well, the chemical potential on this side is given by P2, and this one is given by P1. So let's say this is the solute-free side, so only solvent, and this is the side with the solute. And you already see that what does the presence of the solute do to the chemical potential? It lowers it. Okay, good. And this just comes from this entropy, this mixing part, the TS term. Okay, so now what I can do is I can take a Taylor series expansion of the chemical potential, and what you see is you get a derivative of the chemical potential of the water with respect to the pressure. Okay? And you have this pressure difference that comes into it. Okay, and so now this, the derivative of the chemical potential with respect to the pressure is just the molar volume, the volume per molecule. And if you compare this term, or this expression, to this guy here, you see that the P1 minus P2 term is just this. And that allows you to equate that the P2 minus P1 is NS over volume times KBT. But this is just the concentration of the solute. Okay, so the pressure difference that one sees here, because of the difference in the chemical potential of the water on one side of the membrane versus the other, is related to the concentration. Okay, so just by just considering a system with non-interacting particles, you can basically see where, or understand where the osmotic pressure comes from. Okay, it's clear? Okay, now, what's the concentration? Well, let's think about this. How much pressure would a cell with a concentration of 1 millimolar correspond to? So I have 1 millimolar potassium ions. Right? This is what we talked about right at the beginning of the course. What does that concentration correspond to in terms of a pressure? Huh? First, no. The concentration of, let's say, potassium ions is 1 millimolar in the cell. This guy. Yeah. Okay. So is it, well, does that correspond to a pressure difference of how many atmospheres or pascals or gigapascals? What is it? What's your guess?
What temperature
Let's say room temperature, yeah.
NS is 1 millimolar.
Yeah, so if it helps, I think the number we had was 10 to the 10 ions in a volume of 1 micrometer cube.
Okay, 10 to the 10 ions in
Yeah. Or 10, well, was it 10 to 10? I forget now, no. The number of ions in the cell was, so water was 10 to the 6. No. Proteins was 10 to the 6, ions was about 10 to the 10, water is 10, so this is 10 to the 7, roughly. Yeah, 10 to the 7.
It's a very small pressure.
How much? What does small mean?
I mean,
Is it much smaller than atmospheric pressure? Or bigger than atmospheric pressure?
I think it is much smaller. What's the value of the atmospheric pressure? Isn't it 10 to the 5?
If it's much smaller, I think it will be crushed.
Exactly. Well, so okay, that's true. It certainly cannot be less than atmospheric pressure. For sure, no.
All the unicellular will be.
Isn't atmospheric pressure 10 to the 5?
Well,
No, just think.
just think of one atmosphere.
All amoeba will be crushed, like all the amoebas in the seashore will be crushed.
No, but maybe it depends on the concentration there.
No, so fine. So no.
No, concentration is what gives pressure. So if the pressure
But
is
it's 10 to the 3 to the negative 3.
you said 10 to the minus 3.
Yeah, that's what they're doing.
Molar.
No, you are calculating pressure, right? Given the concentration.
Pressure of difference.
So look, William, NS is about 10 to the 7.
Okay.
Okay? Volume is 1 micrometer cube. So somehow you have to use that information along with molarity and Avogadro's constant, etc., to make an argument. So if you know this, if you know the number of 10 to the 7, you know the volume, you know kBt, you can sort of guess what it should be.
What's the number? And what is the next
You don't need it. I mean, the volume is 1 micrometer cube. Okay? 1 micrometer cube. Actually, in the way that
10 to the 7?
10 to the 7 atmospheres.
No, that's the value I'm getting.
Yeah,
I think
no.
it's per meter square.
But in what units? What does that mean? 10 to the 7 what?
I think it's inverse per meter square.
10 to the power 4 newtons per meter square.
Which is how many?
Isn't that
It's slightly bigger than 1 atmosphere. So Newton's rate is pascals.
It's 0.4 atmosphere.
It should be slightly larger than an atmosphere.
So,
Like twice as large, roughly.
so what is 1 atmosphere in Newton?
10 to the power 5.
10 to the power 5.
Yeah. 10 to the power minus 18.
So you're getting less than an atmosphere.
I got 0.25.
Atmosphere. Okay. Yeah. Okay. It's probably it depends a
Maybe
lot
the number.
on the details of this constant. Okay. But fine. It's on that order. It's on the order of an atmosphere. That's large. But intuitively, it must be, because if you didn't have a osmotic pressure on the order of atmosphere, everything would die.
If it is too large, everything will die.
Sure. So concentration differences in ions create a pressure driving force corresponding to the order of about an atmosphere. It's sizable. Okay? Now, obviously, nature evolved to survive in those types of conditions. So, this makes sense. Okay? Okay. So, yeah, so one could take, different concentrations of different ions in different cells and see more or less how things would compare. But I think you would basically get a very similar answer. So, 1 atmosphere, 2 atmospheres, 3 atmospheres. Okay. Okay, so osmotic pressure is a very important driving force for many biological processes. And which ones? Well, maintaining the chemical potential of water in and out of the cell, for example, is very, very important.
So does that mean that the concentration of these solutes must be very high for animals in the ocean floor?
That's an interesting question. How high does the pressure go underwater?
Becomes too high. It is the number.
But they don't live
They're in the bottom
below.
of the sea.
There is nothing at the bottom of the sea, but
Well,
also
there
there
is
is-
a-
yeah.
There is something.
At the bottom of the sea.
no, there are
At the
some.
bottom of the sea means like up to
On the
where?
beach, I mean.
Not like I can say that there is nothing on the Mariana Trench, like at the deepest level of the sea.
Are you sure?
Yes.
No, I think there is something, some.
There's Hoff.
I think there's some weird things that live there.
Station is in fact still there.
No, most of them no way. There was a kind of a team.
Yeah?
Actually, I don't think people have ever even reached there. So
Yes.
there was a team, I think, led by the director of Titanic. What's his name? James Cameron.
Uh-huh.
He was interested in
Yes.
these things. So they reached pretty deep, but I don't think if they have ever reached that deep.
In which sea?
Hmm?
In which sea do they reach the
I'm pretty sure.
No. See, it has to be the deepest. I think it's in.
I found a topic. I found a topic for you. Life in extreme pressure conditions. Perfect. I'm pretty sure that there's life that survives in those conditions.
Yeah.
It may not be,
Definitely not fish.
yeah, but fish go down to those things in search for food, for
No,
example.
but no, I mean like the deepest from the sea level is almost 11 kilometers.
Yes.
But it's not the same everywhere.
But Nishan, you was National Geographic. Some animals even hide at the bed and we.
No, see, that's what I'm saying. At the bed means doesn't mean at the deepest one.
What do you mean by the deepest?
The sea is like this. So at the deepest one it's 11 kilometers. For example, on the earth, you can't say like someone who lives in Trieste and someone who lives at the top of the Mount Everest. Yeah, that's a different thing.
Let's just wait for your talk.
This-
I mean like
Yeah.
there may be microorganisms and stuff.
Yes.
But fishes, I don't think so.
But-
Crustaceans. Still there.
But okay, so going back to your question, it's a very interesting question. I don't have the answer to this, and it would be interesting to understand and see if the osmotic pressure equilibria is different for things under those extreme conditions. Probably they would be, for sure. For sure. It must be larger. But yeah, I don't know. I don't know. Okay, good. So we're now going to switch gears a bit, and we're still building on our many of the things that we introduced at the beginning of the lectures. I told you a lot about hydrophobicity, I told you a lot about protein folding, but it was more in a biology, physical chemistry language. And now I'm trying to put a bit more of the physics on this, okay? So, Harriet, what's the hydrophobic effect? What? Who doesn't like water? Objects. Okay, and what's the simplest example of this? Or how would you as a physicist measure it? How would you prove to me that I have two solutes, two objects, one is hydrophobic, one is not?
By measuring the fluid.
Okay, very good. Off. The fringe of what? Yes. So that you're right. Measure the free energy to move one object from the, let's say, the gas phase into the liquid. Okay. For a hydrophobic solute, it should be positive. For a hydrophilic, it should be negative. Okay. Okay. So, hydrophobic effects are everywhere, okay? And what we're interested in is biological processes related to hydrophobicity. And as you know, we spent quite a bit of time on this protein folding problem. So the protein folding problem is the problem of taking a chain, a polymer made up of polar, non-polar groups, and it folds into a folded structure. And the common notion, and you remember we showed using that simple lattice model, that if I have two sides, polar, hydrophobic, you can sort of see how if I put hydrophobic groups in contact with each other, I can get folded configurations. Okay, that's what we showed with that simple model. So that's the protein folding problem. That's thought to be driven by hydrophobic effects. Similar thing for things known as micelles. So these are the objects that form, the soap bubbles, of soap foam. Okay? So I have a head that likes water and a tail that hates water, and they try to cluster into this micellar structure. And again, this is driven by hydrophobic effects. But what are the... Okay, this is fine. This is more anecdotal. Okay, but it doesn't have any thermodynamics. What are the thermodynamical signatures of hydrophobicity? Okay, so there are several of them that have been noted. Let me show you the first one. So this is the change in the entropy of a protein upon folding or unfolding. So I have, let's say, two states. The protein undergoes folding or unfolding, and I look at the entropic contribution to that process. And what has been found in numerous experiments measuring the entropic, the change in the entropy, is that for a wide range of proteins, if you look at the change in entropy as a function of temperature, there's a temperature at which the entropy converges. So this is known as the entropy convergence for hydrophobicity. So it's one of the thermodynamic hallmarks of hydrophobicity. So in many hydrophobic proteins, one observes this. And so one of the things we want to ask is why? What causes this to happen? What causes there to be a temperature at which the entropic contributions to unfolding are the same for a whole class of different proteins? Okay, so this is one example of a signature, a thermodynamic signature of hydrophobicity. That's a protein, but we can scale it down and say, how about small hydrophobic solutes? So the simplest hydrophobic solutes you can think of are their inert gases. Okay, so neon, argon, neon? No, I don't even know how to. Xenon, I forget what the name of this guy is.
I think it's not.
No. Neon, argon, and then it's xenon? Krypton, and then, okay. I don't know, what's Me? Book? Manganese is definitely not hydrophobic. Manganese is a transition metal. Okay, but actually, I thought this was this is going to bother me. I need to wait. If I don't figure this out, I'm going to pause. Otherwise, okay. What do you observe? So this is the excess chemical potential, or the change in free energy, to put these rare inert gases in water. So, as you go larger in size, it becomes larger. Make sense? Yes. I'm putting in a bigger solute in water, I have to pay a penalty, bigger penalty. What else do you observe as a function of temperature?
It reaches a peak and then decreases.
It reaches a peak and decreases. And the position of the peak is pretty much similar for all solids. So this is, and actually the derivative of this basically is related to the entropy. Okay? But for solutes, hydrophobic solutes of different sizes, the change in chemical potential or free energy to put them in water, the maximum position occurs at a very similar temperature. Okay, so again, this is a signature of this entropy convergence in hydrophobicity. So, first example was a big protein, a protein that was very complicated. It had not only hydrophobic groups, it had hydrophilic group charges, etc. This is as simple as it gets. Okay, it's inert gas. You still have the same phenomenon. So, where is this coming from? Okay, so that's what we want to try and understand and dig into. So, there have been many theories that have been developed to try and understand hydrophobicity in water. And there are sort of two ideas. One is that there's a length scale dependence to hydrophobicity. So basically, if I put a hydrophobic object, like an oil droplet, in water, then the water around it doesn't like to be near the oil. So the water must do something to make itself happy. Okay? That's exactly the origin of surface tension. Okay, so when I have water and I have air, there's a surface tension, and there's a surface tension because the guys want to hang on to themselves because they can't. It's a very unfavorable interaction with the air, essentially. Okay? And so this idea of doing something with itself is at the heart of understanding the length scale dependence of hydrophobicity. And so the question is hydrophobic effects the same for a small sphere or a large sphere? That's the question. Okay? And so, so let's imagine I put methane or neon. If I put neon in water, this is like putting an impurity. So I put an impurity in the liquid. How much of the liquid is disturbed by the presence of the impurity? So what this argument says is that for a small solute, for a small impurity, the liquid is not disturbed. It just surrounds it and continues to go as normal, business as usual. I grow my impurity up to some critical size. Once I get to some critical size, then I start to disturb my environment. And the question is, what is this critical size? What is this length scale over which you go from this to this? Okay? And so the person who was involved in developing a lot of these theories was a guy known as David Chandler. Chandler is a very nice book in modern statistical mechanics. It's one of my favorites. And so he developed this theory which goes like the following. So I want to ask, what is the free energy to create a cavity in a liquid? Okay, so let's try and look at this a bit more carefully. So let's say I sit myself here in a box, and then I draw a possible spherical cavity around myself. And now I ask, how many particles are there within this sphere? 1, 2, 3, 4. Okay, so over here, 4. Now, the liquid breeds their fluctuations, density fluctuations. Now I go to how many water molecules? 1. Okay. I do the exercise again, and eventually, at some point, I will have 0 waters or particles inside my cavity at a particular radius. Now, if I can count the statistics associated with these fluctuations, then I should be able to ask or answer the question, what is the probability of finding a cavity? Because the probability of finding the cavity is at a particular radius. So I fix the radius, I use either a Monte Carlo or molecular dynamics, whatever I want, look at the fluctuations, count the number of statistics associated with this, and I will get a probability distribution. The probability of finding a cavity is then P of R n equals 0. Okay? And so how might this look? So I have, let's say this is n equals 0, n equals 1, n equals 15, I don't know. And something like this, okay? So this might be, let's say, at r equals 2. Okay, if I make r larger, the radius larger, wait. So let's put this here. So if I make r larger, the average number of water particles in the sphere must increase. But then also, the probability of finding N0 must reduce. Okay, so more or less, I will have points like this. Okay, now if I have this probability distribution, I can get the free energy. Because minus kBt log of this gives me the free energy. So minus kBt log of P of n equals 0 tells me what is the reversible work required to open up a cavity in the liquid. Okay? Now, just to mention why this is all related to hydrophobicity, because this object here is the most hydrophobic object you can think of. So instead of an oil droplet being inside or an impurity being inside, you're self-creating an impurity. So it's creating a void, a cavity, and if I have this cavity form, how does the environment respond to the creation of this cavity? So you should be convinced that I can get this. If I can get this, I can get the free energy. Okay? I'm ignoring any pressure volume contribution to this. And that's okay when I'm working at 1 atmosphere, at ambient pressure. You'd have to go to very, very, very high pressures for the pressure volume term to be relevant to this process.
Excuse me.
Yeah, please.
So free energy is energy minus Ts.
Yeah.
This is just Ts. What about the energy change? Because while we do the Monte Carlo,
Yeah.
we calculate the spin flip and we see the energy change per thing. So between this and
Yeah.
this, so this we may take the most favorable distribution, that is n equal to 2.
Yeah.
So we are, okay, normally if we don't disturb it at a favorable
Yeah.
pressure volume, there will be 2 particles inside the
Yes.
sphere of
Yes.
radius r,
Exactly.
and in the condition that we want, there will be no particles.
Mm-hmm.
So I think the boundary interaction.
There's no interaction, remember.
Okay, there is no
There's
interaction.
no interaction.
That's why the energy term is not taken.
It's a very good question. For this process, at small length scale, entropy is the thing that dominates.
Okay.
Okay? At the short length scale. And then when you start to grow, then things will change.
Because in a lattice system,
Yeah.
we like run Monte Carlo like with this logic.
Yes?
Okay, what is the change in energy
Yes?
for a particular change in the orientation of
Yes.
from this to this?
Yes, yes, yes.
So that is
So okay. So in this case, you can actually extract out what the average change in potential energy is as you go from here to here, and what you would find is at this length scale, the change in potential energy is basically 0. Because so this happens at short length scale just by thermal fluctuations. So most of the contribution of the free energy of is coming from entropy. Most of it. But what we're doing here essentially is you're calculating a constrained partition function in some sense along some coordinate. So remember, the real way to always do these things is to compute the partition function. But you cannot calculate the partition function, the absolute partition function, for the whole system. And it's also not relevant in some sense. Because, for example, in this fluctuation, is it relevant to know what the states of ice are? No. Okay, but if you wanted to compute the partition, you'd have to do that. You'd have to Boltzmann weight configurations involving ice.
Yeah, like if we take the whole phase space,
If we take the whole phase space.
ice will also come.
But that's impossible to do. So what one does is one says, most of the interesting physics is happening in a confined region of the phase space. So I'm going to focus on some projected coordinates along some important degrees of freedom and look at the essentially the constrained partition function and hence constrained free energy along those degrees of freedom only. But that's on one side. On the other side, at the end of the day, this is also mostly driven by entropy. Okay? Okay, so the term in the numerator, delta G, is coming from accumulating statistics of this guy, P of n equals 0. Okay. And so now what David Chandler did is he developed some theory, but then also did some simulations where he plots delta G divided by the surface area of the growing sphere. And he finds that at short length scale, so length scale greater than smaller than 1 nanometer, this is essentially linear. So what does this mean? It means that the free energy to grow the sphere grows as the volume. Because 4 over 3 pi r cubed divided by r squared gives you the r term. And then when you get to some length much larger than 1 nanometer, it becomes constant. Why do you get constant? Because now you have the free energy growing as the surface area. And this value here is essentially the surface tension of your object with an interface with the liquid. Okay, so whenever I want to create an interface, when I want to create a surface, I have to pay an energetic cost. And for a macroscopic object, that cost is related to the surface tension. Okay, so this is interesting. So you have this 2 length scale behavior. And now, this theory assumes only spherical objects. Okay, but fine. We know that there are, fluctuations in liquids which result in inhomogeneities in density that may not be spherical. So the shape may be very different from that of a sphere. Okay, but this is what Chandler came up with. Okay, so 2 length scale crossover regime. Short, volume dependence, long, surface area. Okay, so is this clear? Now, where are we going with this in the context of biology? Well, if I can examine fluctuations of particles leading to the creation of cavities, if I can compute these types of things, then I might be able to say something about hydrophobicity in the context of biological systems. Okay, so that's what we're going to discuss on Thursday. Okay, I think we'll stop now. So please let me know preferably by the end of this week, what you want to talk about on Tuesday.